Azure load balancers distribute incoming traffic across multiple targets, ensuring improved performance and reliability. They operate at layer 4 of the OSI model, managing TCP or UDP traffic to services hosted in virtual machines, containers, or other endpoints. In the context of Azure, load balancers can be internal or public. This design maintains application availability, regardless of the demand level. When combined with other Azure networking features, such as network security groups and private endpoints, Azure load balancers can facilitate secure and efficient traffic distribution. They are fundamental in scaling and safeguarding applications in a dynamic cloud environment. Azure includes two main types of load balancers: a public load balancer for incoming traffic from the internet, and an internal load balancer for private traffic within a virtual network. Public load balancers assign a public IP address to front-end configurations, enabling external requests to reach application backends. Internal load balancers, on the other hand, use a private IP within an Azure virtual network, allowing tier-based applications to route traffic securely without exposing endpoints externally. Feature public LB, internal LB. Access scope internet facing private network, IP allocation, public IP, private IP, common use cases, web front ends, tier-based apps, NSG integration. Yes. A public load balancer is configured to distribute requests from the internet to a pool of Azure resources in one or multiple subnets. To establish a public load balancer, an administrator must create a front-end IP configuration tied to a public IP address. Back-end pool targets, such as virtual machines or virtual machine scale sets, are then assigned. Health probes check the availability of instances in real time, helping the load balancer route traffic only to healthy targets. Load balancing rules specify front-end port and protocol settings, ensuring that inbound traffic is properly forwarded to matched back-end resources. An internal load balancer distributes traffic within a virtual network. It assigns a private IP address to the front-end configuration, making it inaccessible from public endpoints. This approach is beneficial for multi-tier architectures where only specific tiers are publicly exposed. For example, a web layer may be served via an external load balancer, while the application or database layer resides behind an internal load balancer. With private IP assignment, traffic remains confined to trusted network boundaries, relying on custom routes or peering for connectivity. Integration with network security groups strengthens security by controlling allowed inbound or outbound flows. When creating an Azure load balancer, specifying the backend pool is essential to distribute requests among multiple servers. Members can be virtual machine scale sets, individual virtual machines, or application instances deployed in containers. Utilizing availability sets or scale sets enhances fault tolerance within Azure regions. Dynamic changes to the pool are supported, allowing the removal or addition of instances without downtime. It is common to include multiple replicas to handle peak loads and ensure operational continuity. Proper network design, aligning each backend with correct subnets and IP addressing schemes, is critical for consistent and reliable traffic distribution. Health probes monitor the health status of backend endpoints in real time. These probes typically use TCP or HTTP connections to test whether instances are responsive. Administrators define a probe protocol, port, and interval, with a threshold specifying the number of failed attempts before an endpoint is deemed unhealthy. The load balancer stops routing traffic to any resource that fails these checks, enhancing fault isolation and maintaining optimal service availability. Probes can be configured to handle application-level heartbeat signals, allowing advanced detection of partial application failures. Proper tuning of probe settings sustains reliability while minimizing false positive failures. Load balancer rules define how traffic from the front end is distributed to chosen backend instances. They specify protocols, TCP or UDP, port mappings, and session persistence requirements. For example, you can create an HTTP rule that maps port 80 on the front end to port 80 on the back end, ensuring aligned connectivity. Session persistence governs whether each client remains bound to the same backend instance, useful for stateful applications. Additionally, inbound NAT rules can create port mappings configured on the front end to route traffic to designated virtual machine ports. These configurations facilitate precise traffic handling based on application needs. Network security groups, NSGs, regulate the inbound and outbound traffic rules for subnets or network interfaces. When using a public or internal load balancer, verifying NSG settings is vital to enable legitimate traffic. If you place a load balancer's backend pool in a subnet protected by an NSG, you must allow front-end traffic on the correct ports. Internal load balancers can communicate across subnet boundaries, where corresponding NSG protocols must be aligned. Combining NSGs with user-defined routes ensures that traffic flows as intended, blocking undesired traffic while permitting key packets to pass. This approach fortifies network security layers further. Azure load balancers offer high scalability by supporting large volumes of concurrent requests. Integration with virtual machine scale sets automates horizontal scaling, enabling the addition or removal of VMs based on CPU usage or other metrics. Metrics from the Azure Monitor help define auto-scale rules, ensuring enough capacity is available during peak demand. 4. Multi-region redundancy. Combining Azure Traffic Manager with load balancers routes users to the nearest region or a healthy endpoint. This distribution reduces latency and improves reliability. Maintaining synergy between load balancers, scale sets, and application diagnostics helps administrators adapt to changing workloads seamlessly. Configuration of a load balancer can be performed through the Azure portal, Azure CLI, or ARM templates. Below is an example using Azure CLI syntax. Bash AZ network LB create / resource group my resource group / name my load balancer / SKU standard / frontend IP name my frontend / backend pool name my backend pool. After creating the load balancer, additional command define health probes and define load balancing rules or inbound NAT rules. During deployment, attention to subnet placement and IP addressing ensures proper connectivity for front-end and back-end components. This approach aligns with advanced network designs that involve service endpoints or private endpoints in a secure environment.